In Chapters 7, 8, and the inner chapter on molecular orbital theory, we talked about several different ways that a molecule with a leaving group may react with a base or a nucleophile. Each of those pathways involves different sequences of steps, which translate into different considerations we give products. For example, if the leaving group leaves first, we can proceed through an achiral intermediate that can react with either a nucleophile or a base to give an enantiomeric mixture of substitution products or the Zaitsev elimination product. Alternatively, the leaving group and nucleophile can interchange simultaneously, which always results in inverted stereochemistry. Or a base can pull off a proton at the same time as a leaving group, which means that the proton pulled will always be anti-periplanar, which will give us very specific products. We can even have a proton transfer occur before a leaving group leaves, which is very directed and usually involves a proton made more acidic through resonance and an alcohol leaving group. These mostly occur biologically. How can we tell which reactions will proceed by any given mechanism? That's the subject of this chapter. Before we determine what type of mechanism a reaction occurs on, we must first establish on what grounds mechanisms may be competing. If there is a lot of excess energy in a system, the products will seek the most stable form possible. We say this is thermodynamic control, because the product has more thermodynamic stability. If there isn't a whole lot of extra energy, the product's form will depend on the activation energy of the rate-limiting step instead, and once a product is formed, we generally won't go back to the starting material. Notice that in the figure shown, the right side indicates thermodynamic control. The product is lower energy, and it doesn't matter that the transition state is higher energy. The left side indicates kinetic control. The transition state is lower energy, and that determines the product formed, regardless of its energy. Our mechanisms are generally competing under kinetic control, which means that we care mostly about the stability of the transition state and really only the transition state of the rate-limiting step. As a reminder, SN2 mechanisms will have both nucleophiles and electrophiles participated in the rate-limiting step. For this reason, SN2 reactions are affected by factors like nucleophile strength and accessibility of the electrophile. On the other hand, SN1 reactions only have a heterolysis to consider, so only the leaving group and carbocation stability will matter. Similarly, E2 reactions must consider base strength, accessibility of proton, and the anti-periplanar configuration the proton needs to be in. E1 reactions only depend on leaving group and carbocation stability, which you might have noticed is the same factors as SN1. So we already know that some of these factors will help us to differentiate one mechanism from the next. We're going to spend the next little bit looking at each of these factors more in depth. The first of these factors is the strength of the attacking species. That means either the nucleophile or the base. Look at the table shown. Notice that if we take the same electrophile and react it with many different nucleophiles, some nucleophiles are just better. We're going to use the term nucleophilicity to talk about how good something is at being a nucleophile. Before we move on to the next slide, notice that in the sequence of nucleophiles that have negative charge, all of them will give us neutrally charged product and the same iodide. So we can actually guess the shape of the reaction coordinate diagram by the charge stability of the nucleophile alone. Guess what we're going to do on the next couple of slides? Remember though that we aren't looking at the shape to tell what product has more stability. Because we're under kinetic control, we want to know what the transition state looks like instead. The transition state will look mostly like a reactant in exergonic reactions because it's closest to the reactant. It will look mostly like the product in an endergonic reaction, and the more exergonic a reaction is, the more similar the reactant is to the reactants. So if we compare two nucleophiles, then we know that for an exergonic reaction, we care mostly about the relative stability of the reactants, since the transition state looks most like the reactants. How can we tell that a reaction is exergonic? We move the charge from higher on the periodic table, chlorine or bromine, to lower, which is better able to stabilize the negative charge. We use the same rationale to identify chlorine as less stable and therefore having a transition state that looks more like itself and a lower energy barrier. Chlorine will be a better nucleophile, which leads us to an important rule. When the nucleophile is negative, less stable charge makes the reaction faster. Notice that when we compare these two reactions with neutral nucleophiles, the shape of the reaction coordinate diagram changes. This makes sense because we're going from two neutral species to two charged species. Since we are endergonic, the transition state is more like the products, and lower energy products are going to mean a lower energy transition state and a faster reaction. This points at a second consideration. When the nucleophile is neutral, the best nucleophiles will give a result that can stabilize the positive charge better. So now we can revisit our list of relative reaction rates. The slowest two reactions are with neutral nucleophiles, which will generally be endergonic. Negatively charged nucleophiles will be the fastest, with the least stable nucleophiles being the fastest reactions overall. So we know that a nucleophile will generally act slowly by SN2 if it's neutral. We also know that then there is room for an SN1 mechanism of reaction to take place. Remember, SN1 is independent of nucleophile strength, but if you're trying to compare to SN2, a strong nucleophile will favor an SN2 reaction happening and will likely see that SN2. Notice that the strongest nucleophiles in the list below are going to be nucleophiles that are carbon-based. Carbon-based nucleophiles might be very strong, but they need to carry a negative charge. The instances where we can stabilize a negative charge are relatively specialized. We talked about a lot of them in Chapter 7. We talked about some ways that we can stabilize metals as alkylithiums, Grignards, and Gilmans. We can also stabilize negative charge on an alkyne. Remember that alkyne carbons are sp hybridized, and the sp orbitals are 50% s. Because the sp orbitals are closer to the nucleus and lower energy, the negative charge is better stabilized in these sp orbitals. Treating a terminal alkyne, that's an alkyne that's at the end of a molecule, with sodium hydride, forms the alkyne salt with hydrogen as a byproduct. Because the hydride boils off, the nucleophile is left as the only reactive species. So we know that unstable nucleophiles are generally the best nucleophiles. Unfortunately, unstable nucleophiles can usually be stabilized by pulling off any acidic hydrogen. If a strong nucleophile can act as a base, it often will. More on that later. Just like nucleophiles, strong bases generally have less stable negative charge, and weak bases have more stable negative charge. This makes sense if we think about the shape of the reaction coordinate diagram. More stability of bases means a larger energy barrier and a less likely reaction. Just like with the competition between SN1 and SN2 reactions, E2 mechanisms are dependent on base strength, while E1 mechanisms are not. A stronger base will help favor an E2 mechanism over an E1 reaction. So how can we determine whether something will react as a nucleophile or base? Again, we see that instability of charge helps to accelerate both E2 and SN2 reactions. One way to differentiate between SN2 and E2 mechanisms is to take advantage of the location of a reaction. Nucleophiles must react with a carbon, which means that they need to come close to it. In an SN2 reaction, the groups attached to the leaving group cause steric hindrance, another way of saying they get in the way. If we have a base that's large in size, it will prefer to eliminate a proton, which is generally not at that same site and generally not subject to the same spatial constraints. Big bases are therefore usually indicators of an elimination reaction, an E2 reaction. Tert butoxide, neopentoxide, and lithium diisopropylamide, LDA, are all examples of bulky bases that will be used to help favor E2 mechanisms. The more steric hindrance on the electrophile, the more effect the base size has. If a molecule is hindered enough, even ethoxide can function as a steric base. We know that the strength of the attacking species can affect the mechanism of a reaction, but so too can the concentration. If the attacking species is barely present, unimolecular reactions still may occur. For example, hydroxide naturally present in water won't be sufficient to push a bimolecular reaction. Increasing the concentration can push a reaction towards a bimolecular reaction. Leaving group ability also plays an enormous role in the mechanism of a reaction. The more stable a leaving group is on its own, the faster the reaction will occur. Remember that leaving groups are a factor for both unimolecular and bimolecular reactions. However, for unimolecular reactions, the leaving group is much more important since these reactions aren't affected at all by a nucleophile and are going to form most of the shape of the reaction energy coordinate diagram on their own. So if you look at the unimolecular reaction on the bottom, you'll see that the change in leaving group has a much more drastic effect on rate than we see in the top, which is a bimolecular reaction. Also notice that the best leaving groups are those that are conjugate bases of strong acids. So the things on the far right of both tables are sulfuric acid derivatives. Remember that for SN2 mechanisms, typically a negatively charged nucleophile is kicking out a more stable negative charge on a leaving group. This means the transition state looks more like the reactants and less like the products, and is therefore less affected by the leaving group stability. On the other hand, SN1 reactions are inorganic. Their transition states are closer to the products, and therefore the leaving group stability is much more important. More stable charge on the leaving group will always accelerate the reaction. Leaving a carbocation, which is what leaving groups do, is a lot like leaving a hydrogen, which is what bases do. The exact same things that make a molecule a weak base make it a good leaving group. So the best leaving groups are the conjugate bases of strong acids. Practically, the leaving groups that are highlighted here are the only ones that are going to be stable enough to facilitate a substitution mechanism. We can see from the table that hydroxide is too unstable to function as a leaving group, and one might think that we cannot substitute an alcohol. False. We just need to make hydroxide into a better leaving group. It is common to protonate an alcohol with an acid, which makes the leaving group water and leaves behind a nucleophile that can attack. The same considerations apply to alkoxy groups as leaving groups. With a nucleophile alone, we see no reaction. But if we treat with an acid, the ether gets protonated, and now a neutral alcohol is the leaving group. Similarly, alcohols can be difficult to eliminate, especially since a strong base can deprotonate the alcohol and make them even worse leaving groups. Alcohols are actually better eliminated by acidifying them to make a strong leaving group. Since leaving is the rate-limiting step in an E1 reaction, even a weak base can complete the elimination. One might think that we could use a similar method to substitute or eliminate a nitrogen. However, nitrogen is better at stabilizing a positive charge. Because it is more stable, it will take more energy to get it to leave, and it will typically form a stable salt rather than reacting. When we have a leaving group, there are two charges to stabilize. We've talked about stabilizing the negative charge on the leaving group, but we also need to stabilize the positive charge that's left behind. The first thing to note is that those carbons are never sp2 or sp. They are always sp3. This is because we now have an incomplete orbital in an orbital that is functionally more electronegative in each of the cases of sp2 and sp. The more electronegative sp2 and sp orbitals will hold those electrons closer and form tighter bonds, and therefore be harder to leave a charge on. Even if we aren't thinking about a carbocation, which we don't have to in a bimolecular reaction, the extra electron density in the double bond makes it difficult for the extra electron density in a nucleophile to interact. So they don't. So we don't see the double bonds or triple bonds going under either type of substitution. On an sp3 hybridized carbon, substitutions can occur. However, the type of substitution mechanism will depend on the type of carbon. Notice that in an SN1 reaction, shown in the top table, the more substituted a carbon is, primary, secondary, or tertiary, the faster the reaction. In an SN2 mechanism, shown in the bottom table, the reactions are faster with less substituted carbons. The more carbons a carbon is connected to, the more stabilized a carbocation can be. This matters only for unimolecular reactions, SN1 and E1, so tertiary carbons are much faster SN1 or E1 reactions than our less substituted carbons. On the other hand, the SN2 reactions don't ever form a carbocation. Extra carbons on the electrophilic carbon makes the carbon more hindered and actually slow down SN2 reactions. So whether a carbon is primary, secondary, or tertiary will make a very large difference in differentiating unimolecular and bimolecular reactions, particularly for substitutions. This factor is much less pronounced for eliminations. Remember that eliminations occur by the removal of a proton from the carbon next to the leaving group. These protons are much easier to access, and sterics don't play a significant role in determining elimination mechanisms. Sterics can play a huge role in all sorts of chemistry, not just eliminations and substitutions. Sir Fraser Stoddart of Northwestern actually won a Nobel Prize in 2016 for creating a molecular wheel and axle that stays together only because of sterics. This was one of Dr. Vanderwood's professors. Practically speaking, the type of carbon a leaving group is on will determine what type of reactions are realistically feasible. Unimolecular reactions, SN1 and E1, are only possible when the carbocation is sufficiently stabilized, so tertiary, secondary, and only primary when the carbocations would be resonance stabilized. SN2 is generally not possible with a tertiary carbon because of the sterics, but can happen for all other carbon types. E2, since it's unaffected by sterics, can happen on any type of carbon. It just doesn't happen on methyl carbons because there's no carbon next to the leaving group carbon to form the double bond. Anytime a leaving group is on a carbon next to a double bond, resonance structures can greatly stabilize a carbon, making it far more likely to go through a unimolecular reaction, even if it is primary. Solvents can also play a substantial role in determining mechanism. A protic solvent can easily stabilize negative charge with acidic protons, as you can see on the left, while a polar aprotic solvent offers far less stabilization, which you can see on the right. This matters a lot when you think about the reaction coordinate diagram. For SN2 reactions, the rate-limiting step is going to look most like the reactants, which typically includes a negatively charged nucleophile. This means that aprotic solvents will be higher energy and cause faster SN2 reactions, while polar protic solvents will stabilize the nucleophile and prevent it from reacting. On the other hand, SN1 reactions are endergonic and their transition state looks more like the products. Now stabilizing the negatively charged leaving group is more important, which doesn't happen with aprotic solvents, but does occur with polar protic solvents. So polar aprotic solvents are better for SN2, while polar protic solvents are better for SN1. Check out this table, which describes the rates of reaction for an SN2 mechanism in different solvents. See how much slower protic solvents are than aprotic solvents? Much slower. Also, this is a good reminder of some examples of each type of solvent. Water, amines, acids, and alcohols are all protic, while DMSO, DMF, and acetonitrile are examples of aprotic solvents. Again, to illustrate what we just discussed, SN1 reactions are favored by the exact opposite solvent conditions. Protic conditions for an SN1 reaction will cause a much faster reaction. It is worth noting that solvation actually can change nucleophilicity. From one period to the next, solvation reverses trends in nucleophilicity. Higher charge density is going to be more solvated. In polar aprotic solvents, chlorine is faster than bromine, but that flips in a polar protic solvent because the chlorine is more stabilized and therefore less reactive. Within a period, charge density isn't much different in singly charged atoms, so the trend isn't reversed. The less stable charges are still the most reactive in each of these solvents. Temperature is the final factor that we may use to differentiate these mechanisms. But before we understand the effect of temperature, we need to talk about the differentiation in entropy between substitution and elimination. Substitution will result in very little difference in entropy between reactants and products, because a nucleophile and electrophile, two reactants, will form two products, whereas in an elimination, a base and electrophile react to form three product molecules. Since there's an increase in the number of products, there's an associated increase in entropy. Remember that free energy is related to entropy by the equation shown. For this reason, entropy is a much larger factor towards free energy of a reaction when temperature is higher. So in otherwise identical conditions, a molecule reacting at low temperature will have a mixture of substitution and elimination, but a molecule at a higher temperature will more favor the elimination because the entropy is a much bigger factor there. While most substitutions and eliminations occur by the four mechanisms that we've just discussed, Many biological reactions occur through a related mechanism that is very directed and only works because of the stabilization of a neighboring carbonyl. That's a carbon double bond to oxygen. In these cases, the proton becomes acidic enough to be eliminated before anything else happens. While E1, E2, SN1, and SN2 reactions explain many classes of reactions, there are hosts of ways that elementary steps can combine to create products.